Now, scientists have found the strongest evidence yet that a planet 124 light years away could be home to life. Researchers detected molecules in the atmosphere on the K218b.
Imagine a planet 124 light-years away, wrapped in a thick, hydrogen-rich atmosphere, floating somewhere between a super-Earth and a mini-Neptune. For years, it was just another name in a catalogue of distant worlds. But then, something changed. In 2023, NASA's James Webb Space Telescope aimed its eyes at this mysterious planet, K218b. What it saw stunned scientists: traces of methane, carbon dioxide, and even water vapor. A cocktail of gases that, on Earth, can mean one thing: life. Then came whispers of something more, a faint signal buried deep in the data, a chemical called dimethyl sulfide, or DMS. On Earth, DMS is only made by life, specifically microscopic marine organisms. Could we really be seeing signs of alien oceans teeming with something alive? The headlines called it possible life, but behind the scenes, scientists weren't so sure. In this episode, we go beyond the headlines. What did JWST really detect on K218b? Could this be the first hint of alien biology, or are we looking at something else entirely? From the deepest space scans to the quiet skepticism of planetary scientists, this is the untold story of a planet that might just be alive. Most exoplanets we've found fall into familiar categories: gas giants like Jupiter, rocky Earth-like planets, or barren mini-Neptunes. But K218b doesn't fit so neatly. Discovered in 2015 by NASA's Kepler mission, K218b orbits a red dwarf star in the constellation Leo. It's about 124 light-years away, and it immediately caught attention, not because it was just another distant world, but because of where it sits, the habitable zone. That's the cosmic sweet spot where temperatures could allow for liquid water, assuming the right atmospheric conditions. At first glance, K218b looks too big to be Earth-like. It's 2.6 times wider and nearly 9 times more massive than Earth. This would typically classify it as a mini-Neptune, a type of planet with a thick atmosphere of hydrogen and helium, likely unsuitable for life as we know it. But K218b had another surprise in store. In 2019, the Hubble Space Telescope detected water vapor in its atmosphere, a landmark discovery. It was the first time water had been found on a planet in the habitable zone outside our solar system. That alone made it one of the most promising targets for future exploration, but it was the James Webb Space Telescope that would really raise the stakes. In 2023, JWST turned its powerful infrared instruments toward K218b. What it saw sparked a quiet revolution in the scientific community. The data revealed methane and carbon dioxide, molecules that often go hand in hand with biological activity on Earth. And the relative lack of ammonia? That was another interesting piece. It supported a new theory. K218b might not be a mini-Neptune after all, but something much stranger: a Hycean world. Hycean planets are hypothetical water-covered worlds with thick hydrogen-rich atmospheres. They could have warm oceans beneath dense clouds, oceans that, in theory, could support microbial life. If K218b is one of these Hycean worlds, it might be one of the best places in the galaxy to look for life. And then came the real shocker: traces of dimethyl sulfide, or DMS, a molecule produced on Earth exclusively by marine microorganisms. While the signal was faint and unconfirmed, its very presence set off a storm of speculation. Was this the chemical whisper of alien biology, or just noise in the data? Some scientists cautioned restraint, others saw it as the beginning of something monumental, but everyone agreed on one thing: K218b had gone from interesting to absolutely unmissable. The excitement surrounding K218b was electric, maybe too electric. After all, the possibility of detecting life on an exoplanet isn't just big news, it's history-making, and with history comes scrutiny. As news of potential biosignatures, especially dimethyl sulfide, spread through headlines and YouTube thumbnails, many in the scientific community took a step back. They knew what the public didn't. The science wasn't settled. In fact, it had barely begun. Let's break this down. JWST's initial observations revealed water vapor, methane, and carbon dioxide. These are exciting finds. They suggest a complex atmosphere and support the Hycean planet theory. But the DMS detection, that was more complicated. The signal was incredibly faint, buried deep in the infrared spectrum data gathered by JWST's MIRI instrument. And here's the thing, DMS is difficult to detect even on Earth. Its chemical signature is subtle, and in the noisy environment of deep space spectroscopy, even minor errors in modeling can generate false positives. A follow-up analysis led by researchers from multiple institutions, including teams at Cambridge and NASA, took another look. This time, they incorporated JWST's NIRIS and NIR spec data alongside MIRI's readings using new atmospheric models and correction tools. The result? The DMS signal wasn't statistically significant. The data, they argued, didn't support any firm detection of life-related molecules. It was a sobering moment. But this wasn't a failure. This is how science works. Observations are made, models are refined, and conclusions evolve. The fact that DMS appeared in the data at all is fascinating, but extraordinary claims require extraordinary evidence. And right now, the evidence just isn't strong enough. Some scientists also raised concerns about confirmation bias. When a discovery is this exciting, it's easy to see what you want to see. Others pointed to the need for more sophisticated models, ones that can better account for the complex physics of exoplanet atmospheres. And then there's the question of abiotic chemistry. Could non-living processes, like photochemistry or volcanic activity, produce the same signals we associate with life? That's not only possible, it's likely. Despite the disappointment, no one's walking away from K218b. If anything, the debate has made the planet even more interesting. What we're witnessing isn't a gotcha moment. It's the scientific method in real time, and there's something poetic in that. We're trying to read the fingerprints of alien weather patterns on a world 124 light-years away, using instruments that can detect heat from stars formed before the dinosaurs walked Earth. It's messy, difficult, and often uncertain, but it's how we learn. The case of K218b hasn't been closed, far from it. In fact, it may have just set the stage for one of the most profound searches in modern science. The search for life, not as we know it, but as it could be. Let's think about what we're actually trying to do here. We're using a telescope orbiting 1 million miles from Earth to analyze the chemical makeup of a planet over 1 trillion kilometers away. And from that chemical fingerprint, we're trying to guess what's happening on its surface, its clouds, its oceans, maybe even its biology. It's a little like trying to figure out what's cooking in someone's kitchen by sniffing the air from 100 miles away. Still, even that distant sniff has told us something remarkable. K218b likely has an atmosphere. It likely contains water. It may have the right temperatures for life. And most compelling of all, it's different. It challenges the way we define habitable. That's why K218b is now a priority target for future observations. NASA and ESA researchers are planning more detailed scans using JWST's full suite of instruments, not just once, but many times over different seasons and angles. The hope is to reduce noise, rule out false positives, and confirm or refute the presence of biosignature gases. But even if we don't find DMS, even if it turns out to be nothing, that doesn't make K218b less important. It simply means we refine our models. We get better, smarter, closer. And here's where it gets even more exciting. K218b may just be the first of many. Astronomers estimate that billions of planets could fall into this Hycean category, ocean-covered worlds wrapped in thick atmospheres. If even a tiny fraction host life, the implications are staggering. It also raises another question. What if life doesn't need Earth-like conditions at all? What if, somewhere out there, evolution has taken a different path, one that begins not on dry land or shallow seas, but beneath crushing pressure and swirling hydrogen clouds? That's the real impact of K218b. It's not just about one planet, it's about redefining the search, about asking better questions, building better instruments, and preparing ourselves scientifically and psychologically for an answer we might not expect. Because if we do find life, truly find it, it won't look like Hollywood. It might not look like anything we can imagine, but it'll change everything. And it might just start with a signal from a strange little planet orbiting a red dwarf in Leo.